At the end of last time, we looked at or began looking at the Van Hoff equation, which gives the way that the equilibrium constant depends on temperature. It says that the ratio of an equilibrium constant at one temperature to the equilibrium constant at another temperature is given by the delta H of reaction at standard state conditions, and then 1 over the difference between 1 over each of the two temperatures. We saw that there are some general broad implications that follow from this formula. The one is that if the temperature rises, so T2 is greater than T1, and if delta H is positive, that is, if it's an endothermic reaction, then that means that the equilibrium constant will rise with temperature. But on the other hand, if the delta H is negative, so it's an exothermic reaction, then the equilibrium constant will fall with reaction. We saw that we could rationalize that result not just from the equation itself up here, but also by the Le Chatelier principle. In the case of an endothermic reaction, heat is something that's absorbed, so it's a product. And raising the temperature amounts to adding heat to the product side, adding any reactant to the reactant side of a reaction pushes the equilibrium point of the reaction toward the products. That means an increase in K. And so that makes sense. Also, if it's an exothermic reaction, then heat is something that's produced by the reaction. Raising T then amounts to adding a product to the reaction. That pushes the equilibrium back towards the reactants. We also saw that if delta H is a large value, then the equilibrium constant will be sensitive to temperature. But if it's a small value, especially let's suppose that delta H is 0, suppose there were no delta H, then you can see looking up here in the formula that if this is a 0, you just get e to the 0 here, which means that it doesn't depend on temperature at all. So the sensitivity depends on how big delta H is. If delta H is large, then it's sensitive. If delta H is small, then it's negative. Or then it's insensitive, sorry. All right, so let's do some examples now. Let's suppose I have a chemical reaction, A plus B goes to C. Let's suppose that delta H is equal to minus 25 kilojoules per mole. That's a very modest delta H. For most chemical reactions, it's a much bigger value than that. Notice, though, that it's a negative value, which means it's an exothermic reaction, That means that if the temperature goes up from 298 to 310, let's say, we expect the equilibrium constant to go down. So we can get at least that much qualitative information without doing any calculations at all. Now we just have to plug in. So here's our formula. We plug in 25,000 there, 8.314 for R, 310, and 298 for the two temperatures. The initial equilibrium constant was 100. I didn't point that out, but there it is up there. And if you do all the arithmetic up here, that gives you K2 is equal to about 68. In other words, the equilibrium constant has gone down modestly. This is a rather modest temperature rise, only about 12 degrees. And with that modest temperature rise, the equilibrium constant has indeed gone down by a modest amount. Gone down also, just to emphasize that that's in agreement with what we expected from Le Chatelier's principle and from looking at the formula. It's also possible from the information that we have up above, the delta H value and this change in, well, actually the delta H value plus the equilibrium constant at one temperature, to calculate what the delta S value is for the chemical reaction, even if we don't have that by other methods. We can do that by using the fact that delta G0 is equal to minus delta H0 minus T delta S0. And delta G0 here is, of course, related to the equilibrium constant. It's equal to minus RT log of K. And so since we know K, since we know delta H, we can calculate delta S. And that's what I've done here. I've just solved this for delta S. It's equal to delta H minus delta G 0 over T. And then I substitute in minus RT log K for delta G here, and that gives delta H over T plus R log K, big K. Plugging numbers in, that gives a delta S of minus 46.6. All right, so that's really just exercising the formulas, nothing earth-shattering or unexpected about any of that. Here's another example, again for some generic reaction. A plus B goes to C. We know, or we're given, that K increases by a factor of 3. We don't know what K is, but we know that it goes up by a factor of 3 when the temperature changes from 273 to 373. So this is a rather large temperature change for this case. It's a 100-degree temperature change, big enough so that we would be a little worried whether the Van't Hoff equation is valid or not, but we can still do the calculation, even if it turns out, if we have some extra information, maybe it turns out we can see that it's not terribly accurate, but maybe it's okay, who knows. All right, so what is delta H, first of all? This delta, the K actually increases in this case when the temperature also increased. And so that means we know right away that we're going to get a positive value for delta H. It has to be an endothermic reaction because the K increased. It turns out we don't actually need to know K1 or K2 by themselves. It's enough just to know the ratio. So this business of knowing that it increased by a factor of 3, that's good enough. That's all we need to know. Solving for delta H from the Van't Hoff equation, we get minus R log of K2 over K1 divided by the whole thing divided by 1 over T2 minus 1 over T1. Plugging the numbers in, we get 9.3 kilojoules per mole. Notice it's a positive quantity as we knew it had to be from the beginning. Now let's look at how big these changes are. So we've done a couple calculations, but let's see how much change is happening. Let's look at the sensitivity of the reaction, in other words, to temperature change. In the first case, we had a delta G here, a delta H here of 25 kilojoules per mole. I said that was pretty small, but it is still kind of in the ballpark of typical. It isn't horrifically small. It isn't really small. 9 kilojoules per mole, the value we got down in the previous example, that really is pretty small. With a minus 25 kilojoule per mole value for delta H, we saw that in just a 12-degree temperature rise, we got a change of about 30%. And there's a rule of thumb. I'll look down here. Here's the rule of thumb. If a 10-degree change causes about a factor of 2 change in the equilibrium constant, that indicates a delta H value of about plus or minus 50 kilojoules per mole, depending on whether K went up or down. That's the rule of thumb, and it works backwards too. If you know that delta H is about 50 kilojoules per mole, then a 10-degree change will cause about a factor of 2 change in the equilibrium constant. That's kind of what we're seeing here. This is smaller than 50 kilojoules per mole. It's only 25. But we're still, and this is not a factor of 2. It's less than a factor of 2. It's only about a factor of, 0.7 rather than 0.5. But it's still sort of in the ballpark. The rule of thumb is kind of applying here. We can kind of see that with this relatively modest delta H, we should get something less than a factor of 2 for our change in K, and that's in fact what we get. On the other hand, for our next example down here, we have a much bigger temperature rise. So it's a 100-degree temperature rise. So that's 10 steps of 10 degrees. And in that whole business of 10 steps of 10 degrees, we only get a 3x change. Look what should have happened if the rule of thumb worked, right? If we went from 273 to 283, that's a 10-degree rise, we should have gotten a 2x change from that, right? Then if we go to 293, that's another 10-degree rise. We should have gotten another factor of 2, so a total overall of 4x change. If we go to 303, we should have gotten an 8x change, and so on. So you can see that this 10-degree rise, this 100-degree rise, which is 10 steps of 10 degrees each, should have gotten us a factor of 2 to the 10th in the equilibrium constant. I don't even know what that is, but it's big. And so this 3x is way too small for the rule of thumb to be applying. What that tells us is that our delta H must be much smaller than the sort of rule of thumb value of 50 kilojoules per mole. And that's in fact what we find. It's only about 9 kilojoules per mole. So now we get maybe hopefully a little bit of a feeling for how big a given delta H, how big a change in K a given delta H gives rise to. We can also calculate the delta S value from the data we have here. So if we know one of the, in order to get delta S, we actually have to know one of the K values, not just the ratio. In this case, let's suppose K is equal to 10 to the minus 3. At a particular temperature of 373, what is the value of delta S? Well, we can use the formula we derived last time. It's delta H over T plus R log K. We now know delta H is 9,300 divided by 373 plus 8.3.4 times log of 10 to the minus 3, and that gives about minus 32.5 joules per K per mole. All right. Final example, let's look at a Van Hoff plot. If we go way back up here, there's sort of, I wrote down the Van Hoff relationship in 3 different ways. One is the ratio of the equilibrium constants, one is the log of the ratio of the equilibrium constants, and then the third way is this one that gets used for Van Hoff plots. That's what we're going to do now. Notice I pointed out before that if we identify this as y and this as x, then this is the equation for a straight line if we plot the logarithm of k versus 1 over t, and that's the kind of example we're going to do down here. So we have 2 tables of data, well, 1 table of data really, and then we're going to use that table to create this second set of columns. The first raw data has the temperature in one column, values of the equilibrium constant in the other column, and we're moving in temperature by 2 degrees from 300 to 302, 304, 306, 308, 310, and recording, if you like, the value of the equilibrium constant at every point. Notice that as the temperature is increasing, K is going down, so delta H, we know delta H0 is a negative value. This is an exothermic reaction. If we want to make a Van Hoff plot, however, we know that we need to plot log of K on the y-axis and 1 over t on the x-axis, so I use these data to make a new pair of columns. And notice that when you take 1 over 300, you get 0.03, 0.003 actually, and when you take 302, you get something barely different from that, 0.00331, and so on. So things are not changing very much. These are small numbers, and they're also not changing very much. That's characteristic of Van Hoff plots, just a sort of a heads up or a warning. When we take the logarithm of k, the logarithm of 100 is the natural log of 100 is 4.605, and so on all the way down, so k is decreasing. Notice there isn't a huge range in the value of log of k either. That's because when you take the logarithm of any number, the variations get smaller, logs very, very slowly. All right, again, here's our rule of thumb. You can see it operating, especially in this data column over here. By the time we've finished our entire run of collecting data, we've only changed the temperature by 10 degrees, and in that 10-degree change, the equilibrium constant has gone down by almost a factor of 2, about 48% instead of 50%. And that invokes, well, that is consistent with our rule of thumb, which says that a 10-degree change should lead to a factor of 2 if the delta H is in the neighborhood of 50 kilojoules per mole. And so we expect, just from inspecting this data qualitatively, we expect to find a delta H value of near 50 kilojoules per mole. And in fact, we're going to find out that's exactly what it is. Here's my Van 't Hoff plot now. Sometimes I make these plots a good deal cruder. I just draw them out by hand just because that's good enough for lecture purposes. But in this case, I decided to be a little bit nicer and made an actual official plot here. So here is the 1 over t values plotted versus the log k values. First thing to notice is that indeed it is absolutely a straight line. The r squared value for the least squares fit to this data is 1, which means it's a perfect straight line. That's because this is artificial data. This is not true experimental data. This is data I made up. And I made it up using the Van 't Hoff equation in order to get the data, in order to get the k values. And so, of course, it's perfect. It was made to be perfect. Real life does not look like this, just as a warning. You never, ever get data that look like this. This is obviously artificial data. All right. However, you can do a least squares fit to this data, and if you do, then you get a slope of 6008.7. According to Van 't Hoff, the slope should be equal to minus delta h over r, and therefore multiplying the slope by minus r should give us the delta h value, and indeed we get minus 50 kilojoules per mole, exactly 50 kilojoules per mole. It's exactly 50 because that's the way I set it up. Using our standard relationship, we can also, here it is, we can also get the value of delta S. So we now know delta H of minus 50 kilojoules. We choose one of the temperatures. So we've got a whole set of several temperatures here, but we just use one of those temperatures. Any one temperature should give the same value. If everything is working as it shouldn't matter which temperature you use, as long as the temperature you choose is the same, is consistent with the value of the equilibrium constant that you choose. So you got to use them both at the same temperature, of course. And if you plug those numbers in, then you get minus 128.4 joules per K per mole for the delta S. I say that this second calculation is not the best because we have actually 1, 2, 3, 4, 5, 6 data points here, but I only use one of those data points. That means that if in this case it doesn't matter because there's no experimental error, but if there had been experimental error, it would be better to use some sort of average of all these data points in order to make use of all the information, all the data that we actually have. All right, that is it for sort of the main topics of Chapter 10, but there are 2 extra topics that come at the end, and I think they're valuable for a variety of reasons. Those 2 topics are, so we're going to go over them. Those 2 topics are, first of all, using what we know to calculate what fraction of an acid or a base is ionized, and we'll see why that's useful when we get down to the actual example below. But it is extremely useful not only for calculating what fraction of an acid is ionized, but also for calculating what the actual total charge is on a protein. That's the example we'll do below. And also because exactly the same mathematics and logic gets used for any kind of dissociation reaction, right? This is a dissociation reaction. And in biology, there's a bunch of dissociation reactions because there's a bunch of binding reactions, right? Dissociation is just the backwards reaction for any binding reaction. So anytime a protein binds a substrate, a protein binds a ligand, 2 proteins bind each other, a protein binds a DNA, any of those binding type reactions, which is about 90% of all biology, the back reaction from that is the dissociation reaction, and this same logic applies to all those dissociation reactions. So we will use the same logic again when we get to the more biological part of the class, which is what's coming up next, in fact. The other thing we're going to talk about is a simple model for protein folding. The model itself is not of huge interest for its own sake, but the logic that goes into making the model is very, very valuable. It's not hard, using thermodynamics and StatMech, it's really not hard to make actually quite good models for rather complicated situations. The protein folding is a really complicated process, and yet with a very simple model we can get at least sort of the basic raw, rough behavior from protein folding, and we'll see how that works. We'll see how that, what kinds of ideas lead to that. Yeah, so, I mean, the important thing here is to not to learn the details and ins and outs of this particular model, because there are many models. It's to pick up how this was done so that you can do it yourself if the need arises in your future brilliant research careers. All right, so let's look at the fractional ionization problem first. And again, one motive for why you want to do this is, let's suppose you've got a protein. Let's suppose you want to know how that protein is going to move in a gel, right? You're running a gel on proteins or DNA or any of a number of other biomolecules is absolutely a standard thing. But you got to know whether the protein's positively charged or negatively charged. It depends on how you run the gel. Well, if you change the pH, you're ionizing some of these surface groups and protonating some of these other surface groups, and so the total charge on the protein depends on the pH. At one pH, it has a positive charge. Change the pH, and suddenly you can end up with the same protein having a negative charge. Let's see if we can calculate what that charge ought to be as a function of the pH. It turns out we can. So to do that, we begin by defining the fraction of ionized acid. So our chemical reaction, again, is HA goes to H plus A minus. The ionized species is A minus. We want to know, out of all possible A, some of the A is in this form, some of the A is in this form, but out of all possible A, how much of it, or what fraction of it, what percentage of it is in the ionized form? Well, that fraction is just the concentration of the ionized form A minus divided by the total amount of A that's present, which is the sum of the concentrations of the HA and the A minus, that is the unionized A and the ionized A together. If I divide top and bottom here by 1 over A minus, so I divide by A minus on top, I divide by 1 over A minus on bottom. I can always do that, right? Because when I do that on both top and bottom, nothing changes. Then I get that this fraction ionized, this is my definition of what I mean by fraction ionized, but I get that it's equal to 1 over the ratio of the unionized A to the ionized A plus 1. And that's a form we want and can use because we can relate this ratio to the equilibrium constant expression. If this is our chemical reaction, there is an acid dissociation constant, Ka. Hopefully that's familiar to everybody from freshman chemistry. Ka is equal to H plus times A minus divided by HA, using the usual rules for writing down reaction quotients. And notice that the ratio is here, or 1 over that ratio is here. So that means that the ratio of HA over A minus is equal to the ratio of the H plus concentration divided by Ka. It will be convenient, it isn't necessary, I mean this is a good enough answer in a lot of cases all by itself, but it will be convenient to express these concentrations using pH and pKa instead of the concentrations themselves. So pH is equal to minus log of H plus, and that means the H plus concentration is 10 to the minus pH power. Likewise, pKa is minus log of Ka, and that means that Ka itself is 10 to the minus pKa power. So my fraction of ionized A is equal to 1 over H plus over Ka. Now substituting these definitions in and doing a step or two of algebra, I get my final result, at least for this part, which is that the fraction of A minus, or ionized A, HA, is equal to 1 over 1 plus 10. Notice this is not an E. I always kind of, I'm so used to using E as the base for all exponents and logs that I tend to put an E in there, but it's 10 in this case, to the minus the difference between the pH that we happen to be at the moment and the pKa for the acid. So the distance between the current pH, the true pH, and the value of the pKa for the acid determines how much of the acid is ionized. We'll do examples later and see how that works. But before we do that, we want to do the same thing. This was for an acid. If we want to do our problem up here where we're trying to get the total charge on a protein, then we want to do it for bases too, because bases contribute positive charges, and if we want the total charge, we've got to calculate both the positive and the negative charge. So for a base, I'm going to think of the reaction, I'm going to think of the conjugate acid as an acid reaction. So the base is B, but BH plus is the conjugate acid to every base. And that acid will dissociate just like any acid does. It's usually a very weak acid, so it doesn't dissociate much, but it can dissociate. And there's a Ka for that. So when you're describing the properties of a base, it's very frequent to use a Ka value for the conjugate acid rather than use a Kb value for the base itself. I mean, whether you use a Ka or a Kb is kind of a matter of convenience, but it's very common to use Ka values to describe, for example, lysine on a protein, which is in fact a base, not an acid, or normally thought of as a base rather than an acid. All right, so there is a Ka for a base. It's just, you know, the Ka for an acid is something below 7, so something like 4 for a carboxylic acid. And the Ka for a base is something like 9.0 for an amine base, like lysine. And so the only difference, from this point of view, the only difference between an acid and a base is the value of Ka. It's small for an acid, and it's high for a base. So if that's the case, then we can treat the fraction of positive charge, or the fraction of the base that's ionized. But remember, the base that's ionized is the acid itself. It's the equivalent of HA in the old approach, in the acid case, because that's the charged species, right? It's BH plus is the charged species. It's not B that's the charged species. And so the fraction of positive charge, positively charged base, will be BH plus over the total amount of B. And using the same logic, I won't go through it all again, that gives that the fraction of positively charged base is 1 plus 10 to the plus pH minus pKa. Remember for the acid case, for the negative charges, it was 10 to the minus pH minus pKa. Notice it's hardly any different. The only difference between these two cases is this minus sign here versus this plus sign here, and the fact that the Ka value for the base is a large value, whereas the Ka value for an acid is a small value. All right, let's do our example now. Well, before we go on to the example, let's note a couple of things. First of all, if I look at the fraction for the minus charge for the dissociated acid, and the plot for the other case is virtually the same. But if I look at it for the minus case, then as the pH goes up and up and up, the fraction that's in the negative form also goes up and up and up, right? So, and notice this is pH minus pKa, so this value, this point right here, is the point where pH is equal to pKa. So this is not pH 7 here. This is a pH value, whatever happens to the pKa happens to be. If it's a typical organic acid, it'll be around 4. Then as we're raising in pH, which means that we're going from high plus H plus concentration, so stronger acid concentration, to more dilute acid concentration. In other words, as we're lowering the H plus concentration, we're deprotonating the acid, right? If I have a lot of H plus in solution, then I'm going to have mostly HA. That's what's happening down here. In fact, it's all HA. Up here, where there's very little H plus in solution already, it's all in the A minus form. as you would expect. So as the pH rises, we're basically becoming more and more basic, and we're deprotonating the acid, and so you get a lot more A minus. Let's see, what else is worth pointing out? There was something else. Oh, yeah. So this rise is relatively rapid. You can see there's a sort of sigmoidal curve here. And in going from pH of minus 1.5 to a pH of about 1.5, we've gone from completely in the acid form to completely in the dissociated form. So over a matter of 3 pH units, we've completely dissociated. We've gone from completely acid form or protonated form to completely deprotonated form. And the same thing would happen if we looked at it at the base using this other formula. Everything would be reversed. It would be if you were going down in pH, things would turn on, so to speak. But other than that, it's the same story. Another thing worth noting, I already sort of pointed it out here, or I wrote it at least without actually saying anything about it, and that is if the pH is equal to the pKa value, you can see it in the formulas here. If I happen to be at a pH that's equal to the pKa, so if for a typical organic acid pKa is 4.0, and the pH of my solution is also equal to 4.0, then this will be a 0. I'll have 10 to the 0 power here. 10 to the 0 power is 1. This whole denominator is a 2, and I get half dissociated acid. Likewise, if the pH is equal to the pKa of the base, I also get half protonated base. All right, let's do an example now. What is the net charge on a protein with 5 glutamic acids, so those are acidic groups obviously, and 3 lysines on its surface if the pH is 8.5? The pKa for glutamic acid is 4.07. It's got a typical organic acid pKa. And the pKa for the lysine is 8.95, also a very typical value for an amine base. The plus charge, the total plus charge due to all those glutamic acids will then be 5 times whatever the fraction is that are charged, right? So if 10% of it is charged, there'll only be a half of a unit, but if 100% of it is charged, then all of these guys will be on and we'll get 5 units of charge. In this particular case, so we got 5 here over 1 plus 10 to the minus pH minus pKa. Notice that pKa here is 4. pH is far from that. It's 8.5. It's 3.5 units different from the pKa. And that means what? It means we're going to have pretty much, we're way above the pKa. If we go back to our plot up here, we're way out here. We're off the charts. So we're going to get we can see right away qualitatively that we're going to get entirely ionized acid in this case. And in fact, if we look at this 10 to the power part of the expression here, it's 10 to the minus 4.43. That's what happens if you plug the numbers in there. 10 to the minus basically 4.5, which is about 3 times 10 to the minus 4. No, 1/3 times 10 to the minus 4. So it's 3 times 10 to the minus 5. So this is a very small number compared to this 1, which means this denominator is basically 1, which means that it's all of the acid is in the ionized form. It's all in the A minus form. All of those glutamic acids are purely turned on. They're all ionized. Now let's look at the lysines. Again, we have 3 lysines times the fraction of the lysines that are protonated. So that's 3 over 10 now to the plus pH minus pKa. And so we're going to get 10 to the 8.5 minus 8.95. Notice that in this case the pH is quite close to the pKa. That pKa is 8.95 and we're at pH 8.5. So in this case we don't have nearly the big difference between the actual pH and the pKa. And also, there's a plus sign in here, so this 0.5, we have 10 to the 0.5, which is about a 3, which means that this denominator is significant now, Not all of our base is in the protonated form. Not all the base is charged. In other words, a lot of the base is in deprotonated form where it has no charge, where it's neutral. And so of our 3 lysines that are present, only about 2.2 of them actually count. The total charge on the protein then is -5 plus 2.2, or about 2.8. Minus 2.8 is the total charge on the protein. That's a useful calculation to do. There are actually little programs out there on the internet, I think, that do these kinds of calculations for you if you plug in a particular protein and give it the sequence so it can find out how many ionizable groups there are. All right, now this is just sort of fleshing out what I said before. We did it for HA goes to H plus plus A minus, but let's suppose you have a protein that's binding a ligand and now it's dissociating to P plus L. There's an equilibrium constant for that. It's called the dissociation constant, Kd. We can define a P anything, right? So this is PL. This is minus the log of the ligand concentration. We can also define a PKD. And you can see, just making the analogy point by point, that we're going to get, therefore, that the fraction of protein that doesn't have a ligand on it, the fraction of free protein here, is going to be the same thing. It's going to be the same formula as the A minus above for the acid case, and so it's going to be 1 plus 10 to the minus PL minus PKD. And likewise, the fraction of stuff where the ligand is bound is going to be 1 minus that, which is 1 plus 10 to the PL minus PKD. We'll see these formulas again when we start talking about protein-protein binding in the next section of the class. All right. That is the protein, the fraction ionized calculation. You can see we didn't do anything except use all the stuff that we've been learning all along here. There's nothing particularly hard about this, and yet we got a fairly non-intuitive, fairly useful, fairly powerful result. That's the power of thermodynamics and stat mech, especially in biology. Let's look at another example of that kind of thing with this model for protein folding. This is an extremely simple model. There are lots of models for protein folding out there. Whole research careers have gone into modeling protein folding. I can tell you that at least a few years back, protein folding was one of the big areas in all of biophysical chemistry. Lots of people spent lots of man-years and hours working on this problem. This is nothing like some of the more sophisticated models that were developed during that period. It's extremely simple, and yet we can get a lot of information out of it. It gets the basics of protein, some of the basics at least of protein folding. And again, yes, the value of this little chunk of the lecture is to see how this kind of thing can be done, so that when the need comes up or the opportunity comes up when you're later on in your career, you've seen an example and you can do it yourself. All right, protein folding is this. You go from a random coil of amino acids, nothing is sticking to anything else, to some compact structure where everything is sticking to everything else. And the question is, what kinds of free energy changes take place during that protein folding process? Here is the process sort of written out. You have the random coil case where you've got a bunch of amino acids all strung together. Each amino acid has a different side chain, of course. And that string, that random coil, folds itself up, and whereas before the amino acids didn't really interact too much with each other, they're hooked to each other, but they're not actually sticking to each other particularly. In the folded form, they are all sticking to each other. There's all these little weak bonds holding them together. And also, the surrounding solvent, the water, the protein is very exposed in the unfolded state, but not as exposed. Only the surface of the protein is exposed in the folded state. Those are the big changes that occur during the folding process. So what does that mean? Well, if we can get a standard free energy for this folding process, for just one residue of the folding process, then we can calculate an equilibrium constant, right? And from an equilibrium constant, we do all kinds of things. So let's see what we can say or guess about what kinds of contributions to this standard free energy would come from different parts of the protein, different features of the protein as it folds up. Well, first of all, let's think about the interactions between the amino acids. There are hydrogen bonds, there are van der Waals interactions, there are other kinds of interactions between the amino acids. We don't know what all those are, and they're all going to be complicated. And if the sequence of the protein is some particular sequence, then it will depend on that sequence. But we're going to forget about all that. We're going to make things simpler for ourselves. We're just going to adopt an average amount of sticking. And a sticking process, remember, is the delta H part of delta G. Delta G is always delta H minus T delta S. The sticking part, the sticking between amino acids, the sticking between any two things, is a contribution that either causes heat to be put out into the surroundings or causes heat to be absorbed from the surroundings, so it's a contribution to delta H. So this is a contribution to delta H. And we're just going to pick the simplest possible thing. We're going to say it's a certain value for every single residue. Now, in truth, it's a different value for each residue, for each pair of residues, in fact. But we're just going to say that, on average, each residue, once it gets folded up inside the protein, has a certain amount of sticking interactions with its neighbors, and pick one average value for all those possibilities and say it's about 3,000 joules per residue out of a total of N-res residues in the protein. So 3,000 joules per residue when it's folded up. In other words, what we're really saying here is that when it folds up, there are some favorable sticking interactions. The protein likes to stick to itself. It prefers to stick to itself rather than stick to water. Notice that what this change really represents isn't just the amount by which this amino acid sticks to that amino acid. It's the change in sticking between this amino acid interacting with water and that amino acid interacting with water versus the situation where they're interacting with each other, and also maybe a little bit with water. But on average, it's that you have to break amino acid-water interactions in order to form amino acid interactions. And we're saying, well, from experience and from a little bit of fooling around and testing things, we guess that around 3,000 joules per mole is a good value for the average sticking between two amino acids when folding occurs. Another contribution, when the folding occurs, we're going from a free random coil that can take on any configuration to a pretty tight, pretty constrained, relatively stiff structure. And that means we're going to lose chain entropy, right? Every polymer has a whole bunch of entropy when it's in the loose state and a much smaller amount of entropy. The angles between the units on the chain are much more constrained when things are folded up. They're not completely constrained even when they're folded because they can still wiggle around to some extent, but boy, they can wiggle around a whole lot more when they're free than when they're folded up. How are we going to do that? How are we going to account for this entropy change, this chain entropy change? Well, remember that the delta S for any one contribution, as well as the delta S overall, is Kb log W. Well, the S is Kb log W. So S per mole is R log W, and that means the change in S, remember, is the ratio of the number of microstates available to the chain when we're in the final state or the folded state to the number of microstates available to the chain when we're in the unfolded state. And we're going to take these number of microstates to be for just one residue. In the end, we're going to multiply this delta S by the number of residues. So this ratio of microstates is meant to be the change in the ratio in the number of microstates available for one residue when it's folded versus when it's unfolded. And we're going to say, again, this value is kind of picked post facto by experience. We're going to say that there's about 6 times as many microstates available when the system is in its unfolded state, when a residue is in the unfolded state, versus when it's in the folded state. So we lose a factor of 6 in microstates for every residue when the system folds. That's what we're saying. And then there's one more contribution. Now again, there's only 3 contributions in this model. A more serious model would have a lot more contributions, and we'd worry about the sequence of the protein and everything. But in this simple model we're just going to have these 3 contributions. And that comes from the hydrophobic effect, which is a very subtle and really rather complicated thing, but for our purposes, we're going to say that the hydrophobic effect is due to changes in the freedom of water to rotate. In other words, this is an effect that comes from the solvent. It's not from the protein itself. And it's not the sticking of the solvent to the protein either. It's the freedom of the water to rotate when it's exposed to the protein versus when it's less exposed to the protein because the protein is folded up and some of the residues are buried inside the protein now. So let's talk about that. Here's the value we're going to use in the end. The ratio of states before and after is 4, 2 to the 2 power, per polar residue. This doesn't apply for the non-polar residues, but does apply to the polar ones. I'll talk about where that comes from in a second, but let's talk about the hydrophobic effect itself first. Like I said before, it's rather complicated, but the main contribution seems to be the following. I said it's water rotational states, but what does that mean? It means the following. Let's suppose our chain is composed entirely of non-polar residues for the moment. So the polar residues are different, but for the non-polar residues, when the water right at the surface, right at the interface between the bulk water and the protein chain, those waters are looking, if you like, for opportunities to hydrogen bond with the chain. Well, on a nonpolar residue, there are some opportunities, but there's relatively few of them. Nonpolar residues have a big nonpolar side chain, for example, in each case. And that doesn't give the water any opportunities for hydrogen bonding. What that means is that the water can hydrogen bond only with its neighboring waters. And that means that statistically, in this layer here of waters that's next to the hydrophobic molecule, the waters tend to be oriented with their little hydrogen bond donor hydrogens pointed outward. The waters face out, and that means they're partially oriented. Their rotational freedom is less than it would be if they were in the bulk. And what all that means is that waters that are near the interface with a hydrophobic or non-polar surface of any kind, whether it's amino acids or if it's an oil droplet or anything else that's hydrophobic, then their rotational freedom is reduced, the number of rotational microstates available to them is reduced compared to when they fold up, right? Here the protein is completely unfolded. There's lots of surface area of contact between the water and all the amino acid residues. Fold it up, and there's less surface area of contact. Some of those residues are now partially buried, right? This whole interior surface is buried. And if this were a bigger protein, it would be even more, right? You'd have all the interior residues completely buried, water exposed only on the surface, and therefore less restriction or constraint on the rotational degrees of freedom for the water in the folded state than in the unfolded state. All right, so what we're going to say is that the ratio of microstates available when it's folded versus when it's unfolded is 2 states per water molecule. We're going to say that there are 2 water molecules in contact with every amino acid residue as it folds up. And so it's 2 per states raised to the 2 power because of 2 waters. And again, this only applies to nonpolar residues, not to polar residues. All right, so that's the model, or that's the logic behind the model. Let's put it all together now. We're saying that there's a delta H contribution due to the sticking, minus 3,000 joules per residue of protein, no matter how many proteins there are, no matter how many residues there are. We're saying that the delta S contributions to delta G has 2 contributions. One is from the chain entropy, the restriction of the chain entropy when it folds up. One is from the hydrophobic effect, right? This is unfavorable. We lose microstates here. Up here, notice we're gaining microstates, right? There's more microstates in the folded state because the waters have more microstates than in the unfolded state. So there's a favorable contribution due to the hydrophobic effect. The unfavorable chain contribution is the number of residues times R times the log of the ratio of the 2 W's, and that's 1/6, so it's minus number of residues times R times the log of 6. For the hydrophobic effect, it's half the residues we're going to say. We're saying that half of the residues are hydrophobic or nonpolar. So there's a half in here, times R, times log of the ratio of the 2 W's, and that becomes a plus n residues times R times log of 2. All right, putting all those terms together, we get the following, that our delta G now in our model, this is our model value for delta G, per residue is minus 3,000 minus, this is delta H, right, minus T delta S. So this is delta S. This is delta H. Minus T times a minus R log 6 plus R log 2. We can combine these logs, and it all boils down to something extremely simple. It's minus 3,000 plus RT log of 3. So all these ideas that we were looking at, that we put into our model, boil down to an expression for how the delta G depends on temperature. That's really extremely simple in the end. Let's do a calculation now. Depends on the temperature, of course, so we choose 300 K, our standard temperature. If we plug that number in, we get that the net delta G, the net change in Gibbs free energy per residue at 300 K is equal to just, in this end almost is canceled by this end, and we get only about minus 260 joules per mole. Is that a lot or a little? It's small, right? Why is it small? Because the thing we're always going to compare any of our delta G values to is the value of RT. That's the energy available in the surroundings. That's 2,500 joules per mole at 300 K. And so this is only about 1/10 of that, right? The delta G divided by RT is only about 1/10. And that means that per residue, there's very little sticking energy. And let me say that though this came out of our calculation, this is also in agreement with experiment. So the fact is that proteins do fold, and they fold spontaneously, and that means that there's a favorable delta G for folding. But per residue, it's pretty small. The driving force for folding proteins is not very large per residue. What that means is that you've got to get a whole bunch of residues folding at once in order to get a big enough delta G, a big enough favorable delta G, so that it doesn't just shake back apart from thermal energy in the next instant. And so, if you've got 100 residues in your protein, and they all fold at once, so the protein goes from completely unfolded to completely folded all in one step, and it more or less does a lot of the time, a lot of like that. Then you've got a delta G that's minus 2,600, not 260, right? 100 times bigger than 260, minus 2,600 joules per mole. That's big. That's big enough. That's much bigger than RT, 10 times bigger than RG. And so that's big enough to make the final folded protein be stable. Another thing we can do is calculate, all right, that was true at 300 K, but what if we start changing the temperature? At some point, what's going to happen if we look at this formula here, you can see we've got a favorable negative contribution from the delta H's. We've got a net unfavorable contribution from the delta S, right? The loss of chain entropy is actually enough to give us, is the dominant thing, right? There's also the hydrophobic effect that's favorable, but the chain entropy is even more unfavorable, so this whole term is positive and therefore unfavorable. That means that if we keep raising the temperature, making this unfavorable term bigger and bigger, eventually delta G is going to go to 0 and the thing's going to unfold. And the question is, at what temperature will that happen? Well, we want the line or the melting temperature where delta G goes to 0, where the ratio or the population of folded and unfolded proteins should be the same. And so we set delta G equal to 0 and we solve for T. The melting temperature, so-called melting temperature, that's going to be 3,000 divided by R log 3, and that turns out to be 328 K, or about 55 degrees C. That's pretty typical, in fact, for proteins. And so our very simple model explains two things to us. One is the cooperativity of proteins, of protein folding. The fact that they do tend to fold as an all or nothing kind of process and also unfold as an all or nothing kind of process. They don't fold a little bit and then stop and then go back and stuff. They fold or they don't fold. That's explained by our model. And the other thing that's explained or predicted by our model is some sort of estimate for the melting temperature. And you know, we didn't pick a particular protein here, and there are variations in melting temperatures from protein to protein, or denaturation temperatures, if you like, from protein to protein. But this is a pretty typical one, so also good. We could go on to ask some more questions. We could say, what happens if all of the residues were nonpolar? We chose half the residues to be nonpolar. What if they all were? What would the protein behave like in that case? Or what if they were, none of them were nonpolar? What if they were all polar? What would happen in that case? Well, you can kind of imagine qualitatively, but the model helps you see at what point. Then, you know, you can see that if all of them are polar, the protein isn't going to fold. There isn't going to be any driving force for folding. On the other hand, if all of them are, if none of them are polar, they're all nonpolar, then it's going to fold pretty hard, and then it might be hard to melt. We can investigate those questions with the model. Another set of questions is, what happens if we choose or change some of our values, right? So we chose sticking energies of minus 3,000. We chose chain entropy change, or WF over WU, folded over unfolded, to be 1/6. What if that isn't quite right? Or what if we put in some amino acid residues that have a different value for this? We can also ask about what happens if we start changing the parameter for the hydrophobic effect and so on, and see what kind of behavior we would expect for that. That helps us explain trends that we may see in the behavior of actual proteins. All right, with that, we are done pretty much with the pure basic background on thermodynamics and stat mech for this class. The next section of the class is going to be about applications to biological systems. There are, of course, a ton of them, and so we'll take that up next.